guys. I'll share my screen. Here it is. No, that's not it. Where's the paper? I think if I just do this and then, wait, where is the paper? Sorry, guys, technical difficulties. I do this, and then you should just be able to. Here it is. Okay, can you guys see the paper or no?
Yeah, oh, good.
Okay, cool. Thanks. So I just want to introduce the paper briefly and what it's about, but actually then I'm going to go into like a little bit of a revision of linear algebra, which is a bit ironic because I've actually never taken a class on linear algebra, but hopefully I do some justice to it because I think a lot of why this technique works or like why it's useful is because of it, like the techniques that are used, which are based on linear algebra. So anyway, this paper is about spectral normalization, which the authors introduce as a way of regularizing your neural network. And it's specifically applied to generative adversarial networks or GANs. And that's because GANs are notoriously hard to train. Like you have to do like a massive hyperparameter search when you're training GANs, because a lot of the times when you're training them, they'll go unstable and you'll basically have to start again from scratch with a different set of hyperparameters, which means that it's almost like a part of training GANs is random search where you're just guessing what to do. And at the same time, GANs are very powerful generative networks, which means that you can use them to learn like a data distribution and then come up with new samples. I mean, that's the thing they're most famous for, is their ability to create like very high fidelity samples of something. For example, if we go down to the appendix, like here are generated samples from their model of like pizza. Let's see if we can zoom in and see some like how weird the examples are. I mean, they're not great, but from afar they look like pizza, right? And actually, the reason why this paper, I think, became so popular is because the author of the original paper on GANs, Ian Goodfellow, he read this paper and thought it was really interesting, and also that the technique itself was very, like the results were very powerful because the authors were able to train a single generative model to come up with examples, like pretty good examples of images, like samples from almost I think every single class within a data set that has 1,000 classes. Like basically they were able to come up with a good sample for every single class in ImageNet. And that kind of diversity especially is something that's hard because of how GANs are trained. I guess, but before we go into how GANs are trained, I wanted to do like this kind of look at linear algebra real quick, just to, because I was hoping that everyone had that in the back of their mind when we talk about GANs and why this method is so successful. So I need to find, hopefully it's here. Yeah, okay. So let's just think about a matrix. So a matrix is a linear mapping from one vector space to another. I think that's true. And one of the key characteristics or properties of a matrix is its rank, which is the number of linearly independent columns in the matrix, or in its column space, it's called. And in the context of neural networks, the linear independence of those vectors is kind of like the number of features that matrix is extracting from the input information. So if you have like 10 linearly independent vectors, or like the matrix is of rank 10, then it's calculating essentially 10 features that are different from each other. But if you have two vectors that are not linearly independent, then they're just calculating the same feature, but maybe have like a different magnitude in terms of like the output vector that's coming out of it. So to me, you could think of the rank as like the number of features that are being extracted. And so having a linear mapping that is high rank, like a matrix that is high rank, is good for neural networks because, and each layer in a neural network, I think most of us know, is like usually a linear mapping and then a non-linear activation function. So having a matrix that has like a high rank means that you're extracting a lot of information from your input features. And you want that to like propagate a lot of information, hopefully through your, or have the ability to propagate a lot of information through these matrices so that you can learn a lot of like either higher order features or just like maintain a lot of the input information when you're making decisions on the output of the network, like which class something is. So one component of this paper that's important, that I think that they say is important, is that you maintain having weight matrices that have high ranks within your neural network. There's another element to this, which is that for any matrix, not only square matrices, you can calculate the singular value decomposition of that matrix. Key component, there's two elements to the singular, well, there's three, but like, I guess a way that I would think of the singular value decomposition in this context is it has like the singular value, which is some value, like in this case, they're showing you sigma 1 and sigma 2 in this diagram. And then like there's a vector associated with it, which is pointing in some direction. The vector is the like the feature that we were talking about before. And the singular value is the magnitude of the output vector. Like in this case, it's showing you like how much you stretch the input vector that you get in a specific direction. And so the other component is that I think in this paper, they argue that the singular values, like their relative size, indicates the importance of different features. And I think what they argue in this paper is that having both a high rank weight matrix, but one that has like that is also can also learn to just have singular values of different size instead of having singular values that are all the same value, which is one of the baselines that they compare it to, are both important. Having a high rank is so that you can have feature diversity, but then also having being able to have relatively sized singular values is important because it allows you to discriminate like the importance of features. So anyway, that's my quick intro or back into, yeah.
The sigma matrix is a square matrix, right? Or
yeah. Yes. Wait, no. Is it? I don't think it's a square matrix. It's just a diagonal matrix. Let me see.
But yeah. Would you have to be square in order to have a diagonal? Otherwise, it becomes.
No, sigma is it says a n by n rectangular diagonal matrix. Yeah,
there are some sort of schemes for approximation where you essentially you make sigma smaller and therefore essentially cut out noise of your vector spaces. So this is kind of cool, right?
That's like a low rank approximation. I think that you use sort of less singular values. Then you can have like you can have a feature reduction, I guess. Yeah. Just have less.
So it doesn't have to be square. That's good to keep in mind.
Yeah, the singular value, but I think I had the same question. It was like, how can you have a rectangular diagonal matrix? I think it just means that the maximum rank of your method, your model, I mean, of a matrix can be actually that makes sense, the number of columns it has. So
yeah, you pad it with zeros.
Yeah, you'll never have it like, you'll never have a, yeah, anyway.
Okay, so you can think of it as generalization from eigenvalues. In case of an eigenvalue, the original matrix is square, and in general, singular SVD creates a non-square diagonal matrix with singular values. However, that also means that you can actually do the truncated version, which is equivalent to this, and then end up with a square matrix with diagonal. Because you can extend it and make if it's not square, you can extend the matrix with zeros on the diagonal, and then you can also cut down the extra singular vectors on either side, right?
Right, because the zeros you add, they essentially fall out again because multiplication by zero is zero anyways, right? So
yeah, exactly.
You always put it back to a square form.
You can also show that if it's a non-square matrix, if you multiply with itself, if you do, can you mute Peter? Because I think it is, because we are in the same room.
Oh, sorry.
They're sitting opposite each other. Right. So if you do like a ATA and then you do eigenvalue decomposition on that, you will get eigenvalues which are the squares of the singular values of A, I think, right? So they are really, SVD is a generalization from eigenvalue decomposition, if it helps, right? And then you can also see the same with the diagrams Peter was showing, except here you have two directions, right? You have left singular vectors and right singular vectors.
Would they be squares? That feels odd, right? Because that would mean that singular values can only be positive. Is that true?
No, eigenvalues are positive.
No, eigenvalues can also be negative.
No, singular value are positive, yes.
Not if you do ATA, right? If you do ATA, then the eigenvalues will be...
ATA, yeah. That's the square matrix. Sorry, yeah, you're right.
But it says over here that singular values are non-negative real numbers. So there's going to be non-negative. But anyway, hopefully the part of this that less the technique of singular value decomposition and more just like the two components to keep in mind for like, I guess why the authors argue that this technique works is one, maintaining singular values in your weight matrix that are they're not all the same, and at the same time having a high rank. Maintaining non-zero singular values that are not all the same, and maintaining a high rank for your weight matrix. So now I have to go back to where is it? Here. Okay, so keep that in the back of your mind, and we'll talk about GANs now. So GANs are they're a very unique, I think, training technique for learning generative models, and they're composed of two separate networks. One is a generative network, and one a discriminative network. The way that training a GAN works is that so you have your data set of examples like images from CFAR 10, and you feed it into your discriminator as a positive example, saying this is a real image, so you want to classify it as such. That's what your discriminator is doing, saying real versus generated image. And then you have a generative model, which usually it samples from a prior, which is like a Gaussian distribution, like not a multivariate Gaussian distribution, or it's an isotropic. Usually it's like an isotropic multivariate Gaussian distribution. So like just has a single value that parameterizes its entire covariance matrix, and it's a diagonal covariance matrix. So you just sample from that, you feed it through the through the generator, and then it creates an image, and then you feed that through the discriminator, and then it should say that the discriminator should say that this is a fake image. And the whole point of the way that GANs are trained is that you take turns training the discriminator and the generative model. So I think it says it over here. Where does it say it? Well, here it says GANs are a framework to produce a model distribution that mimics a given target distribution, and it consists of a generator that produces a model distribution and a discriminator that distinguishes between the model distribution from the target distribution. But you take turns to training the discriminator and then the generator. And I think, I don't remember which one comes first, but it doesn't really matter because they're iterative. So like usually you take like 10 steps with one and then you take 10 steps with the other where you're updating one and then the other. And that's because you can only, it has to do with the reason why you do this is because like if you train, I think one too much with while not updating the other, then you fall into a lot of the failure cases of GANs. And so here's where they talk about some of the failures or the difficulties of GANs down here. They say the discriminator is often inaccurate and unstable during training. So it has a lot of trouble distinguishing between the generated images and the actual images during training. And then also it just like at some point becomes unstable, which means I guess it either stops learning or it learns something like it starts learning in the opposite direction where it becomes worse at discriminating between them. And then it says the generated model network fails to learn the multimodal structure of the target distribution. So yeah, the main failure case I've heard with generative with GANs is that the generative model just learns to, like, for example, a single class or a single image of a single class, because if you think about it, if you can memorize a single image from your data set of images, your generative model can memorize a single image, then it will have completely achieved its goal of being able to mimic at least some part of the target distribution. And so you have to usually add in like some additional either objectives or I think the training method that they use in order to stop it from learning what they call mode collapse, which was it can't learn like multiple classes or multiple examples. And then they say even worse, when the support of the model distribution and the support target distribution are disjoint, there exists a discriminator that can perfectly distinguish the model distribution from the target. So if you start generating images, if your generative model is so bad that it starts generating images that essentially look nothing like the data set that you're training with, then it becomes really easy for your discriminator to tell the difference between the two. And at that point, that means that because their supports are disjoint, the gradient with respect to I think it says once such a discriminator is produced in this situation, the training of the generator comes to a complete stop because the derivative of the so-called discriminator with respect to the input turns out to be 0. So if it's like perfect, if it's perfect, the discriminator is perfect, then you can't train the generator. And so it's almost like you have to have an imperfect discriminator to train the generator. And so all of this is what they say, this motivates us to introduce some form of restriction to the choice of discriminator. So to like regularize the discriminator in some way. One thing I think is really interesting is that, like I said before, one of the main things that interested people in this paper originally was the fact that they were able, like the generative models produced were able to produce examples, like interesting examples for every class in a 1,000 class data set, which means that they're regularizing the discriminator, but it's allowing them to learn a better generator, even though they're not doing anything to the generator. And that's because you have to propagate the gradients through the discriminator to get to the generator when you're training it. Okay. So the two key ideas that they say are important for the results they get are that they only have a single hyperparameter that they're adding to the training algorithm, which is the Lipschitz constant, and that its implementation is like the implementation of their method is simple and it has little additional computation costs. The main claim that they have for their method, they don't actually talk that much about the diversity of examples that they're able to produce. The main claim that they have for their method is that it makes training GANs more robust to hyperparameters. So it's less likely to hit one of the failure cases of GANs when you're using this method than other methods. So let's get into it. Unless I'm just going to check if there's any questions. No, okay. So we talked a little bit, well, anyway, we'll talk about it. So here they're introducing GANs, and I like that they have like a pretty technical explanation, or not a technical, they have a pretty in-depth explanation of GANs. So they just assume that the networks that are being used in the discriminator or that are a sequence of linear, like weight matrices and nonlinear activation functions. And then the output of the nonlinear, the last layer is it goes through a activation function they call like mathcal A, which is an activation function corresponding to the divergence of distance measure of the user's choice. This, I think, if anyone else read this paper in a lot more depth, I was like, this is really confusing to me, because a distance measure is something that is between two things, and the input, and also the divergence of a distance measure is a measure between two things, and this function only takes one thing in as an input. So I didn't understand how it could be the divergence of a distance metric. But anyway, then I read farther down and they say here the activation function mathcal A is just usually the sigmoid function, which makes sense. You know, it's trying to say like, it's a binary classification of whether this is a real example or not. But if anyone has an explanation of why that last activation function, if it's a sigmoid function, is a divergence of distance measure, I'd be interested. Anyway, and then they say it is known for a fixed generative model, G, the optimal discriminator for their, oh, sorry, I should introduce this. So the whole, for training GANs, the objective function is you have some objective function V, and it takes in the discriminator and the generator, and you want to maximize like the value of this objective function with respect to the discriminator and minimize it with respect to the generator. And you can see the objective function that's commonly used over here, which is like you want to it's essentially saying maximize the probability of the discriminator saying that it's a true example for true examples, and minimize the probability of the discriminator saying that it's a true example for fake examples generated by your discriminative model. And so they show you over here that the optimal discriminative model for this objective function is one that is able to basically tell you the ratio of likelihood. Is it the ratio? Not the ratio, but basically this fraction where it's like the likelihood of an example Q with respect to the target data set, and then divided by the likelihood with respect to the target data set plus the generative models data set. So that's what the optimal discriminator is. So that's again, and then it's objective function. And then over here, let's see. A number of works advocate the importance of Lipschitz continuity in assuring the boundedness of statistics. So essentially, there's cases where you can, like for example, if either of these values is 0, then your like your optimal discriminator value, like the probability outputted by the model is unbounded. Oh, there's a question. So they're saying Lipschitz continuity makes the model, the function, like the discriminator more robust because it allows it to basically not estimate unbounded statistics. It says corresponding to, Vahan says, it says corresponding to the divergence of the distance measure. I think it means that the measure function depends on the activation function, not that the activation function is a distance measure. That makes sense to me. So anyway, here they introduced their spectral normalization method because the whole point of spectral normalization is to create an upper bound for the Lipschitz continuity of the discriminator, where the Lipschitz continuity, we'll go into it in a second, and what that does is it stops you from, like it bounds the statistics that you're estimating when you're training a discriminator. Says we follow in the footsteps of yeah, with okay. So they're saying this was like their initial motivation for looking at Lipschitz continuity. So what is Lipschitz continuity? It's defined over here, up here. And it's saying that basically if there's a difference between two inputs, and then you pass them through some function, that the difference between the two function outputs is bounded by some m, which is less than infinity, where m is like the Lipschitz continuity constant of the function. And it's the smallest value. So it's like the smallest value or like the maximum change you can see between two outputs. Let's say. Okay, now they're talking here. The thing I highlighted is just talking about, they're talking about how their method is different than previous work, but I think their related work section is a better look at that. So, okay, I feel like I'm going through this in a back and forth manner, but I hope I've just said we introduced GANs, and then they said Lipschitz continuity is a good way to keep GANs from going unstable because it helps bound the statistics you're estimating. And then the way that we enforce Lipschitz, like an upper bound on Lipschitz continuity, is through spectral normalization. That's what they're introducing here. And they basically tell you how to calculate the spectral to normalize the, or sorry. What they show over here is that for a weight matrix A, the singular value of that, the largest singular value of that weight matrix is its Lipschitz constant, or Lipschitz constant. And so if you want to normalize it so it has a upper bounded Lipschitz continuity, then you calculate its largest singular value and you divide the weight matrix by it. So sigma of A is the spectral norm, and that is its largest singular value. And this is what they do to bound the largest singular value of a weight matrix to, in this case, 1. And then they show over here with equation 7 that the Lipschitz constant of the whole neural network F is upper bounded by the product of the Lipschitz constants of each of its weight matrices. And so if you're able to set the Lipschitz constant of each of the weight matrices to 1, then the whole function's Lipschitz constant is upper bounded by 1. And yeah, that's what they're, and so this is how they're ensuring that the Lipschitz constant of the discriminator is 1 or less, and that's how they're upper bounding it.
Yeah, can't you always say that you don't want one value to explode, but you probably don't want them all to go to 0 either, and this normalization sort of prevents both.
That's true.
If it's smaller than 1, you would expect it to go smaller and smaller and smaller as you go through the network, but this way you sort of say that it's at least more likely that there's one path through it that doesn't go to 0, so it should make it more stable as well.
Yeah, that's the sensitivity part of it, where you want the model to be more. I agree with that, but I think because they can only show an upper bound and not a lower bound.
Yeah, of course, yeah.
They can't show that, but I agree with that, and I feel like a lot of the explanation of why this value is this method is valuable, like for example that is based on that idea. Let's see.
Well, one thing I found quite funny, what is the sigma called between 2 layers? The
activation
spectral
function.
Oh, yeah, or the larger singular value, right? So is that one depends a little bit on the dimensionality of the layers, right? So if you because by default the layers are not all the same dimension, right? So if I think correctly, then the L2 norm between different layers would naturally be sort of different, right? So that you would say that if you have a 1-1-1 vector in a 3-dimensional representation, the L2 norm is different than a 1-1 vector in a 2-dimensional representation, right? So would that mean that the that is essentially the average activation per layer is being sort of like moderated by the size of the layer. You would think that if I have a layer that is very large, like at the beginning, the average activation should be lower, but it should be sort of increasing as I make the network deeper, so to speak.
I don't understand how. Are you talking about the singular values or the activation functions?
Oh, the sigma of A, right?
The sigma of A is just it's a scalar.
Yes,
and
and we set it to 1 essentially, right?
No, you calculate it to set the spectral to set the singular value, because you divide by the largest singular value, and then that means the largest singular value of the matrix is 1.
Of course, and if you then calculate the sigma again, it should be 1, right?
Yeah.
Exactly. Now you go from a 2-layer to a 3-layer, then in order for that to be true, then the average activation in that layer has to become smaller, right? Because you have essentially more values over which you.
I see what you're saying.
Calculate.
So you're
I'm not
saying,
sure whether that's true, actually. Yeah.
I think the only thing that's true is that.
Oh no, because you can always rotate it, right, into 1 0 0 0 0 components essentially. Never mind then.
I think what I'm understanding from what you're saying is, like, say you have a matrix that has a rank of 2. That means that it has 2 values where one has a singular value larger than the other. And now you're upper bounding the largest one by 1. And you know that they're non-negative numbers. So that means that the other one has to be 1 or less, but it has to, if you have 10 value, but also the ratio of the 2 matters for, like, saying which feature is more important. If you have 10, that means you have 10 values that one has to be less than the other. So maybe, like, you're going to have small, as you get a larger rank, if you're in a larger and larger rank matrix, you're going to get smaller and smaller singular values, just so that you can have discrimination between which ones are important.
Actually, probably not. I think it's the S and V part of the S and D part of the singular value decomposition, right? That essentially rotate, right? So you can always, I think, rotate in such a way that it's really the singular value itself that matters. So it doesn't mean that on average the activations have to go down, but rather, I think you could still have technically in each layer an activation of 1 somewhere and 0s everywhere else, and have a singular value of 1, just because that 1 vector gets rotated into the next layer's 1 vector, even though the layer size might be very, very different. I think I was just wrong. Never mind.
Okay. I think I didn't fully understand what you're talking about.
I was wondering, but I was wondering whether normalization actually affects the average activation in each layer in terms based on layer size, but I don't think it does actually.
Okay. What do you mean by average activation?
Like the typical size of each layer's value, so to speak.
Okay. So, like, if you took the L norm of the output of that layer, what magnitude it would have? Yeah,
you compare the L norm of one layer to the L norm of another layer, right? And because the layers have different dimensions, it's not entirely obvious that it's dimensionality independent. But because the rank is typically lower than dimension anyways, it doesn't matter, because any change due to dimension essentially gets rotated out and is not touching the singular values anyways. So I think that's why it becomes independent of the dimension of your layers.
Okay. I think that makes sense. I'm not going to get into this now, because like I said, they mention works that are similar to theirs quite a few times, but I think the section that talks about it is best. So they've just shown you how to upper bound the Lipschitz constant of the discriminator in section 2.1. In 2.2, they tell you how do you calculate the largest singular value of the spectral norm, because you have to do a singular value decomposition in theory to do it. but you can actually use something called power iteration instead to calculate the largest singular value, which is also how they calculate like the eigenvalue. I think the largest eigenvalue of a matrix usually. So it's just using that same method. And what's interesting is if you look at the appendix, like the whole idea of power iteration is that you keep multiplying like a vector by the matrix essentially. And the more times you do it, the more accurately you can estimate like the largest eigenvector and then such the largest eigenvalue. But they assume that there's the change in the weight matrix between steps is really small. So they only perform one iteration of power iteration to calculate at each step the largest singular value. So it's really computationally efficient because they only do one matrix multiplication in this method in order to calculate the spectral norm. It's kind of cool. So anyway, yeah.
Just wanted to add some more stuff about power iteration. So they do it because if you calculate all singular values, it will be cubic or almost cubic complexity. So with power iteration, the theoretical complexity is square, I think, but in practice, it's actually almost linear. I did some experiments a while back. It's like it's funny because it's matrix vector multiplication. It's so optimized. It's basically almost a constant line, which is why it's very important, right? Because you need to calculate those a lot, and it's important for their algorithm also because you need only to calculate the largest singular value, which makes the whole thing achievable, I guess.
Yep. In Appendix A, they go over the power iteration method they use if you guys are interested. And then the last step is they say, how do you calculate the gradient with respect to calculating the spectral norm? And it's all here in equations 9 through 12. The only part of it that I want to highlight is over here, they say, so let's look at equation 12. It has two terms on the right-hand side. And they say, we would like to comment on the implication of 12. The first term, this, is the same as the derivative of the weight matrix without normalization. So the first term is essentially the normal gradient of that layer. And they say, in this light, the second term in the expression can be seen, so this is their interpretation, as the regularization term penalizing the first singular value components with the adaptive regularization coefficient lambda. Lambda is positive when delta and this are pointing in similar directions. And this prevents the column space of W from concentrating into one particular direction in the course of training. So I guess the way I understood that, so it says, in other words, spectral normalization prevents the transformation of each layer from becoming too sensitive in one direction. My understanding of that is almost like saying that I think if a weight matrix becomes too sensitive one direction, then that's almost equivalent to being like of rank 1. That's my understanding of it, where you basically have like a single direction or a single feature that has such higher magnitude than all the other ones, that all the other ones are kind of like blanked out by that. And so they're basically saying that this regularization term helps enforce feature diversity. But that's my interpretation of this. I'm stating it in case anyone has like another take, or whether they agree with that or disagree with that, to see what you think.
Wouldn't that be exactly what the mode collapse essentially is? That your data set sort of moves into the one direction that is maybe easiest to generate or discriminate against, and then kind of get stuck? Yeah,
I think that's true. What's interesting though is that this gradient is only for the discriminator, not the generator, and the generator is what leads to mode collapse. But I was thinking maybe the idea is that if your discriminator only concentrates on a small number of features to discriminate between data points, then possibly it leads to mode collapse in the generator, because it only has to like basically create a specific set of sub features in order to that the discriminator is concentrating on it in order to like even. Yeah,
exactly. Any change that the generator does that is sort of orthogonal to that maximum discriminative direction has no impact on any results. So even if it happens randomly, it's on average, you know, zeroes out, and the net movement then goes towards one of these major components.
Yeah. And then they talk about spectral normalization versus a number of other techniques out there. The first one is weight normalization, and they say it's a method that normalizes the L2 norm of each row vector in the weight matrix, and they basically say that therefore up to the scalar, this is the same as Frobenius normalization, which requires the sum of the squared singular values to be 1. And they're basically saying these normalizations, however, inadvertently impose much stronger constraints on the weight matrix than intended. And it says using such a, and they have an explanation, but they say using such a weight matrix corresponds to using only one feature to discriminate the model probability distribution from the target. So it's basically saying that it's almost equivalent to making the weight matrix of rank 1. And they say in order to retain as much norm of the input as possible, and hence to make the discriminator more sensitive, one needs to make the norm of this large. And so they're saying, basically, with this method, I don't want to keep reading out. It's saying that there's a trade-off between like sensitivity of the model and rank of the model. So if you want to have a model that has a high sensitivity, then it needs to have a high, this value, which is activation times weight matrix, needs to be large. But if it's large, then the weight matrix is most likely going to be of rank 1. So it's not going to like have a very high discriminative power because it's only going to have one feature that it's learning essentially. So they're saying that's the fallback of this weight normalization method. And then the second method they talk about is, they also say the same is true of weight clipping, which is another method they look into. And then on the other side of it, so the first weight normalization method, it produces low ranked matrices, which is a problem. On the other side, they have orthonormal regularization, which does the opposite. It produces matrices that have like a very high rank, but they argue that because orthonormal organization destroys the information about the spectrum, which is the ratio of singular values, essentially, by setting all of the singular values to 1, then I guess it loses some discriminative power or something along those lines, because you can't discriminate between you can't say which feature is more important than the other based on its singular value. So you have these two competing baselines which have these unintended negative impacts, and they argue that their method is able to doesn't have them and is able to take advantage of both of the positive elements of these two methods. And then they also talk about using a gradient penalty in combination with a Wasserstein GAN. And let's see, because they say the approach has an obvious weakness of being heavily dependent on the support of the current generative distribution. So I guess the problem with these gradient penalty methods is that they, if the generative model's distribution support, like the distribution is learning, the support goes away from the discriminative model, you have the same problem that you had before, or something along those lines. Anyway, they say this can destabilize the effect of such regularizations, and also it costs more. So I'm not going to go too much into this. I haven't had a lot of time to think about what they mean here, but basically this method also has some issue, and it has a high computational cost. Let's go to experiments. So they do experiments on 3 data sets, CFAR10, STL10. I think both of those have 10 classes, and ImageNet, which has 1,000 classes. And I'm not going to, they go through how, like the specifics of how they train each model. I'm not going to go into that. And then they first show the results on CFAR10 and STL10. And you can see them over here. So the first experiment they did has to do with how robust their method is with respect to all the other methods in terms of hyperparameters and choosing hyperparameters. And specifically, it seems like models tend to go really unstable when you have high learning rates. So you'll notice that D, E, and F. So the hyperparameters they're using for Atom, this is like Atom, alpha is the learning rate, beta 1 and beta 2 is the momentum coefficients of Atom, and then NDIS is the number of updates they do to the discriminative function between updating the generative function. So anyway, what you can see is on CFAR10 and CFAR10 on the left, their method is the one all the way to the right, which is SN, and then these are all of the baselines they compared it to, that it has like the most high inception score. For inception score, but higher is better. It has like on average the highest values. That's the point they're trying to make. So it's like most robust. And then they show the same thing for STL10. Maybe it would have been better, although probably not as cool looking a plot if they had just shown the average value, because here it's like kind of hard to tell between orthonormal and spectral normalization, like for CFAR10, which one is better. Obviously, orthonormal did better in its optimal case. So that's their first thing. They're showing more robust than other methods. And then the second experiment, let's see over here. Oh, this is just, it's like friendship something distance. Let's see what the metric is called. It's another method for estimating the quality of generated images. Anyway, FID, we'll call it FID for now. If you're interested, look it up. And then over here, so in table 2, they don't only want to compare like the average performance, they're comparing the best performance of their method versus other methods. And they show on both data sets that their spectral normalization GANs with ResNet architecture included with the standard CNN has the best performance. So not only do they have their most robust hyperparameter tuning, but they also have the most robust performance. So that's their second result. Their third result, I actually really like these plots, and I think they highlight a major difference between different methods. So they show over here weight normalization, weight clipping, and spectral normalization. And it's a little bit hard to read, so let's just focus on layer 1 on the top right. I mean, the top left. Basically, the first layer has 26 columns, and they are they calculate the singular values of the 26 columns, and they order them where the right of the plot has the largest singular value, and they've normalized all the singular values to 1. And what you can basically see is that layer 1 for spectral normalization has a ton more high value singular values, which means like a ton more features that have a high, that are like a ton more features, like a higher rank matrix essentially than the other two. So here you can see that at least for the first 5 layers on CFAR10, and then all of the layers on CFAR on STL10, that they have the matrices that you're learning are much higher ranked than in the other 2 cases. It would have been interesting to compare it to like the orthonormal basis. I mean, the orthonormal regularization, because they did say in the method that weight normalization and weight clipping suffer from this issue of learning very low rank matrices essentially. But anyway,
interesting to see what happened between layer 5 and 6, why suddenly there seems to be like also sort of collapse, right? I mean, it's still a bit in layer 7, it still has a bit more spectral weight spread out over Hang on. Oh, no, it's not purely visual, right? Because the number of the index size is still the same between layer 5 and 6.
Hmm.
But between 6 and 7, it's not, which
Yeah.
is strange, right? It looks almost like between 6 and 7, the spectral density has spread out again.
Hmm.
Because it's double the size of base dimension.
Yeah.
I don't know.
Yeah, I don't know what happened. I was thinking maybe this was just like, maybe this was with ResNet or something like that, and it's like, it had, by layer 5, it had learned the discriminative features it needed to distinguish between real examples and fake examples. And so after that point, it was just using those, like a feature based on those to do the discrimination, you know, like something along those lines. But I have no idea. That was just a guess.
That might be interesting to tell you something about the problem itself. I don't know whether this would be like reproducible from run to run, or whether yeah, how particular this is to the data set you're looking at. That might be actually tell you something about the data itself, which could be quite an interesting diagnostic.
That's true. I wonder, this is a paper from 4 years ago, so maybe they've done something like that. Or yeah. And then let's see. Okay. And then the last result is just where they compare orthonormal regularization to spectral normalization. And they basically show that their performance of their method doesn't, what was it? It was like, I'll just look at what I highlighted to. It says, as we predicted, the performance of orthonormal regularization deteriorates as we increase the dimensions of the feature map at the final layer. So I guess that because there's no spectrum, like all of the singular values of in the orthonormal case are 1, as you increase the number of dimensions in the final layer, the orthonormal case fails, just probably because you can't really distinguish between which features in terms of return, which is important based on the magnitude of each feature, something along those lines. So they also show how, I think they, in the previous plot we showed how it's better than weight normalization and weight clipping, and this one is showing how it's better than orthonormal regularization. Yeah, and then the last thing that they have, which is they don't show any results for, but they just, we looked at them a little bit before, is that where is it? On ImageNet, they're able to create like really good examples of 100 different classes, or 1,000 different classes, which is rare. So yeah, that's the paper. But it was a interesting technique and an interesting look at like maybe why neural networks behave in certain ways, or like how, in this case, how you can stop failure cases from occurring when training GANs. Does anyone have any questions or final comments? We're almost done today, so feel free to shout out anything. If not, we can finish early.
I have a question. This might be a bit stupid, but doesn't sort of constraining your discriminator to be Lipschitz continuous reduce the hypothesis space of the discriminator?
Yep, but that's the whole point, that if they argue that if you let the discriminative model be too expressive, essentially like having a really large function space of functions that it can learn from, that it will quickly learn to go to one of the failure cases where it, like, for example, that the generator might start generating, have a different support than the target distribution, and then the discriminator will work perfectly, and then you have to stop training. So by regularizing it, you're forcing it to live within a specific realm of functions that is more constrained, but stops it from failing. And so it's more robust in this sense, in terms of like the hyperparameters that you use to train it.
I think the ultimate problem why that is, or why that is a good solution is because your data is always finite and granular. And so technically there's always some minimum distance between your data points, and that smoothing sort of takes that away, I think, and means you have essentially a well-posed problem.
Yeah, that makes sense. Thank you.
Well,
Peter, I really enjoyed the linear algebra recap. I think we need more of those things.
yeah, I was honestly thinking about it for like a good maybe 15 minutes. I was like, how do I understand in like in an intuitive sense what this paper is doing? I hope that was correct what I was saying, but yeah.
Oh, very good, really good.
Nice. Well, thanks everyone for coming, and hopefully we'll see you next week. And everyone have a good weekend.
Thank you.
You too.
Thanks,
Bye.
Peter.